Welcome back, everyone. In this segment, we will continue our discussion about finding area, about integration in general, other applications of integration and evaluating integrals. And I have quite a bit of topics here to cover. So what I'm going to do is I'm going to again break it down into two separate segments. So we're going to begin the segment with something I should have done in the last one, but I forgot, which is indefinite integrals. So we looked at in the last segment how to find area using the shortcut method known as the fundamental theorem. We evaluated integrals that have limits of integration, right? But I want you to know that from time to time, you might also be given just a problem that is an integral question with no limits of integration. So let's begin with that. So how do you handle those cases? So for instance, say you want to integrate this function, 5x squared plus 3x minus 7. If there is no limits of integration, basically what this is it is a practice on finding antiderivatives. There's nothing to plug in, right? So this is just a new notation that we're using. When we did antiderivatives, we used the capital F notation. So this one simply would be like, take the antiderivative term by term, 5x to the 3 over 3 plus 3x squared over 2 minus 7x, which is the antiderivative of minus 7. And then here we would put the plus c. You might say, why didn't we use plus c when we're doing definite integrals, when we had limits of integration? And the reason for that is, you could have had the plus c, then minus c, they would have canceled anyway. So with definite integrals, we don't even bother putting the plus c. But if there's no limits of integration, we're going to still keep that as we did with the regular section on antiderivatives. So let's do this one. So to anti-differentiate 5 over x squared, I'm going to first write it as 5x to the negative 2. And so apply the power rule there for anti-differentiation. So add 1 to the power. It'll be power of negative 1 divided by the new power. And this one I can write as 4x to the 1/2. And the antiderivative will be 4x to the 3/2 divided by 3/2. Plus c. And if we simplify everything a little bit, we're going to have negative 5 over x. And if you flip this multiply with the top, you can have 4 times 2/3. In other words, 8/3 x to the 3/2 plus c. So nothing different. It's just I want you to be familiar with the notation of integration. If you have limits of integration, we have learned how to do it using the fundamental theorem. You plug in the upper limit minus the lower limit into the antiderivative. Otherwise, just take the antiderivative. Like this one right here, integral of 5 sine x dx. So take the 5 out, integral of sine x. Okay, which function has as its derivative sine x dx? So cosine would have been negative sine, right? So you would take negative cosine, and that should do it. So its answer is going to be negative 5 cosine x plus c. And similarly, for the example at the bottom, let's think about a function whose derivative is secant square. That would be tangent, right? And let's take the 6 out. So this is the same as 6 times the integral of secant square x dx. And that turns out to be 6 times tangent x plus c. All right, so now that we have clarified that, let us take a look at let me go back to my goals here. So the next thing we're going to do is understand how to find area under a curve when you have a function that is not entirely positive, something that goes to the positive side, negative side, it alternates between positive and negative. How do we find area in that situation? So just to remind everybody, we had learned this theorem to find area under a curve when the function is positive. So you integrate from a to b f of x dx if you're trying to find area under f of x, and if f of x is positive, right? But what if it's not? So in that situation, let's say you have a situation such as this, a function f of x where part of the time it's above the x-axis, part of the time it's below the x-axis. In that situation, we need to take basically absolute value of all the separate areas and add them up. And it would help to find, first of all, the x-intercepts of the function. Then you're going to integrate it in segments, like integrate from a to b, then from b to c, then from C to D. And notice here, this between B and C, the function is negative. It's below the x-axis. There, the heights of your rectangles would have been negative. Therefore, when you do the integration, it's going to be a negative answer. But if the question says find the total area between the f of x and the x-axis over the given interval, you're going to have to take the absolute value of that and add it to the other two areas which are already positive. So in general, you would find the x-intercepts of the function, integrate it between the x-intercepts, and then add up the absolute values of all the results. The positive regions already, you don't need to put absolute value, but the negative regions is where the absolute value would really be important. So for example, say we have a situation like this. Say you already know the integral from a to b is 2, integral from b to c of this function is -5, and integral from c to d is 6. What is the total shaded area? So the integral itself is negative, right, between b and c, but the area can never be negative. So you would take the absolute value of that quantity, which is +5, and you would add up all those numbers together. So total shaded area would be 2 plus absolute value of -5 plus 6. In other words, 2 plus 5 plus 6, and that's 13. On the other hand, if the question says, what is the area, not area, but just the integral. What is the integral from a to d of f of x dx? There, the question didn't refer to area, it just said integration, right? In that situation, there is no reason to take absolute values. So that would be 2 plus -5 plus 6, and that will be 3. And in physics, you might use concepts like this to find total distance traveled versus total displacement. So like if somebody leaves the house, let's say goes 100 meters that way, and then returns 50 meters that way, let's say returns 60 meters that way. Okay, so 100 meters that way and returns 60 meters that way, the total distance that person walked or traveled is like 160 meters, right? But what is the total displacement? Where is the person at in comparison to where the person started at the beginning of the problem? Let's say if this is the home, they're only 40 meters away, right? So in one of the cases, even though this is +100, this is -60, to find the total distance traveled, you are adding the absolute values of the results to see how far this person traveled. But in the other case, if one is +100, one is -60, you're actually adding the values with the signs preceding them because you want to find a total displacement. In that case, the person is 40 feet away. So similar ideas like that, that may use area under a curve. Sometimes you need to find absolute values. Sometimes you use it without the absolute values. And here's our first example where we have to do all the work. It's not going to be given to us necessarily what the integral is between points A and B like it was in the example above. So it's in a problem like this, f of x equals x squared minus 4x, and we're supposed to find the area between the function and the x-axis over the interval from 0 to 5. I gave a hint here saying graph first to see the region. But even if that hint is not given, if the question asks you to find area, you ought to always look at the region first. Because if the region is sometimes positive, sometimes negative, you're going to have to split it and do in sub-intervals. So you can look at the graph of this using your calculator. But if you factor x out of there, x times x minus 4, you're going to see that it has two x-intercepts at 0 and 4. And this is a parabola that opens up. So roughly speaking, you have an idea what the graph is going to look like, and it crosses the x-axis at 0 and 4, and we want to find the area between the function and the x-axis all the way to 5. So this is one area, plus this is another area that we're going to need to find. And again, what I did here was I set x squared minus 4x equal to 0, and from there I factored out an x, and I set each factor equal to 0 to get x equals 0 or x equals 4 as the x-intercepts of this function. So to find the total area that is shaded, we're going to need to find in two segments, integrate from 0 to 4. And do you expect that to be positive or negative? If you said negative, you are correct. That integral is going to be negative. We're going to take the absolute value of that, and then you're going to integrate from 4 to 5, the same function. Do you think that is going to be positive or negative? That one will be positive, right? And then we're going to add the two results, the absolute value of this to that result to find the total shaded area. So let's get started. So first I'm going to integrate the function from 0 to 4 to find the area between the x-axis and the function over that region. So x squared minus 4x dx. And the antiderivative is x cubed over 3 minus 4x squared over 2, which is minus 2x squared. Limits are 0 to 4. Plugging 4 in, we're going to get 64 thirds minus 2 times 16, or 32. Minus plug in 0, you get nothing, right? And here I can get common denominators to simplify this. And if you simplify it, you're going to end up getting negative 32 thirds. 64 minus 96 all over 3. That's negative 32 thirds. Now we expected to get a negative answer, but the area will be absolute value of that number. So the area will be positive 32 over 3. Okay, keep that aside. Also do the integral from 4 to 5 of the same function, x squared minus 4x. So the antiderivative is exactly the same, right? So the antiderivative is going to be x cubed minus 2x squared. Excuse me, x cubed over 3 over 2x squared. Going from 4 to 5. So as always, we plug in the upper limit first to get 125 thirds minus 2 times 25 minus, open a parenthesis. Okay, here you want to go ahead and plug in a 4 into x. Now, if you recall, we already did that part up there. We plugged in a 4 and we had gotten negative 32 thirds. So I'm just going to use that value from there. So now I have a positive because there was another negative up front. So positive 32 thirds. And so starting with 125 over 3 minus 50 plus 32 over 3. And we can simplify a little bit, like I can add 125 plus 32 all over 3 to get 137 over 3. And then minus 50. Let's see, what did I do there? 157, sorry. 157, because 125 plus 32 is indeed 157 over 3 minus 50. So now I get common denominators. So 157 minus 50 all over 157 minus 150 all over 3, and that gives us 7 over 3. So there it is, our area, the total. Okay, this is the area actually from 4 to 5, not so fast. I should not circle that just yet. So the total area is going to be the sum of the two areas. So the area from 4 to 5, we expected to get positive. Indeed, we got a positive. And the other side, when we took the absolute value, we had 32 thirds. And now let's add those up to find the final answer for the entire shaded region, right? And that's 39 thirds or 13. So that is our final answer for this question. So step number 1, find your x-intercepts. As a matter of fact, step number 0, graph the function, look at the region. If it's always positive, like something like this, you don't need to split it apart. You could just find the x-intercepts here and integrate it from this x-intercept to that x-intercept, right? Because it's above the x-axis all along. But if it alternates, sometimes positive, sometimes negative, in that situation, you would need to split it into regions and add up the absolute values. So here's another example for you to think about. And this would be a great point to pause the video and come back, check your results. The function is x cubed minus 4x. We're going to find the area between the function and the x-axis from -1 to 2. And here you have a rough graph And we see that sometimes the graph is positive, sometimes it's negative. So we're going to have to do this in segments. Integrate from -1 to 0, right? And then integrate from 0 to 2 and add up the absolute values of the two answers. So let me give you a moment to do this. So I do hope you took a moment to try to set this up. Again, the region in question was a region such as this one. And if you don't know exactly where you cross the x-axis, you should set your function equal to 0 at first. In this situation, I can take out an x, and then x squared minus 4 can be factored further as x minus 2x plus 2. There are 3 x-intercepts at 0, at -2, and at +2. But of those, really the only ones that matter, because our interval begins at -1, is -1 to 0 and then 0 to 2. And we expect, if I call this a sub 1, this a sub 2, we expect a sub 2 to be a negative result, and of which we're going to take the absolute value. Okay, so let's begin. Let's do the area 1. First, I'm going to find the integral, and then I'm going to take the absolute value as necessary. Although in area 1, we don't need the absolute value. We expect that to be positive. So integrate from the left endpoint to the right endpoint. That's from -1 to 0 of the function x cubed minus 4x. By taking the entire derivative of x cubed, we get x to the 4 over 4. And the entire derivative of -4x is -4x squared over 2, which is that's -2x squared, and evaluate it from -1 to 0. Now, as always, plug in the upper limit in first. Plug in the 0 for x, and you're going to have 0. So you're going to have 0 minus, now plug in the lower limit of -1. Everywhere you see an x, -1 to the 4th is +1. So we're going to have 1 over 4. Or basically, we have a 0 when you plug in the first quantity into both of them. That's just 0. Minus, plug in -1 into the second, plug in -1 into everywhere you see an x. So -1 to the 4th will be +1. So you have 1/4 minus 2 times. Again, -1 to the second power is +1. So you're going to have -2 times 1, or -2. Now distribute your negative sign that's outside of both of those, right? So it'll be -1/4 plus 2, or 2 minus 1/4, or 7/4. So we expected to get a positive answer there, and we got a positive answer. So that's the first area. The second area, we must integrate from 0 to 2. So take the same exact function, just integrate from 0 to 2. It'll be the same exact entire derivative, right? Nothing changed there as above. X to the 4 over 4 minus 2x squared. Plug in the upper limit in first. 2 to the 4 is 16. 16 over 4 is 4. And then plug 2 into the second quantity. 2 squared is 4. 4 times 2 is 8, so it'll be minus 8. And then plug in the lower limit where you see an x. You get nothing. That's minus 0. So here we have 4 minus 8, or -4. But remember, this is where we had to take the absolute value. So absolute value turns out to be +4. To finish the question, we must add the two absolute values. 7/4 plus 4, that will be our final answer there. So, I don't know what happened to my, let me move everything up a little bit. So the sum of the two areas will be 4 plus 7/4. And at that point, you can get common denominators, multiply the 4 top and bottom by 4 to get the same denominator as this one. So you're going to have 16 plus 7 on the top and 4 on the bottom. So 23 over 4 will be our final answer. So if the question says area, do not do it blindly. You must look at the graph first, decide if you have to split it into subregions, and only then you will be able to figure out the area by adding the absolute values of the subregions areas. Okay, with that, let us take a look at our next topics for today. But there are some really good examples in your group activity 3.2. You may want to do these examples, 3B, 4A, and 4C, as good practice questions on finding area for functions that change sign, that become positive and negative throughout the given region. All right, so another practice I'd like to go over in this segment is practicing integration with trigonometric functions. Again, especially those of you moving on to Calc 2, you're going to see that quite a bit. So let's take a look at a few practice questions using trigonometric functions. And again, this might actually be nothing too unusual here. So if you feel comfortable, this is something you could try first and then come back and look at the results that we have. In each case, we're going to take the antiderivative and plug in the upper limit minus the lower limit. Please note, this question does not refer to area. It's just a practice question on integration. As we did in the last segment, if that is the question, just to practice integration, then you don't have to graph it. You don't have to see if it's positive or negative, and the answer can be positive, the answer can be negative. You should not be taking absolute values. Only when the question says find area, we do those types of things. Okay, so for this one, let's just take antiderivatives one by one. Antiderivative of 1 is x, antiderivative of cosine is sine x, because derivative of sine is cosine, right? Going from 0 to pi, plug in the upper limit for x, you get pi plus sine of pi, and then minus, plug in 0 for x, 0 plus sine of 0. Now this is entirely 0. Sine pi is 0, so we just get our final answer is just pi. So it's really good to know your unit circle so you can answer simple questions like sine pi or sine pi over 2. But if you're a little bit rusty, you could make sure that your calculator is in reading mode when you're doing those. But for well-known angles like that, I would highly recommend you review your unit circle. Okay, the next one, integral of 3 secant squared t dt. So the antiderivative will be 3 tangent of t, right? That's the antiderivative of secant squared. And we're going from 0 to pi over 4. And if you plug in pi over 4 for t, you're going to get 3 times tangent of pi over 4 minus 3 times tangent of 0. Since sine of 0 is 0, and tangent is sine over cosine, this one will be 0. Tangent of 0 is 0. And do you remember what tangent of pi over 4 or tangent of 45 degrees is? That's where sine and cosine are the same and their ratio is 1, right? So tangent pi over 4 is 1. We get 3 times 1 or 3. Okay, what about the next one? Antiderivative of cosine of 5 theta d theta, everything multiplied by 3. First of all, I can take the 3 outside. And cosine of 5 theta, the entire derivative will be sine of 5 theta divided by 5. In differentiation, we multiply by that constant. In anti-differentiation, we divide by that constant. This one did not have any limits of integration, so we're just going to leave it like that. 3 over 5 times sine of 5 theta plus c. So this is another way to write it. And it's important to remember, integral of cosine is sine, but integral of sine is negative cosine. So the plus minus signs reverse in anti-differentiation, right? And how do you find the entire derivative of secant times tangent? Here we have integral of 4 secant u tangent u du. Take the 4 outside of the integral. And which function has as its derivative secant times tangent? If you said secant, you are correct. And we want to evaluate from 0 to pi over 3. And if you plug in the upper limit, so secant of pi over 3. And if you like, you could factor the 4 outside. So it's going to be 4 times, open parenthesis, secant pi over 3 minus secant of 0 when you plug in the lower limit. And that'll be 4 times parenthesis. Okay, pi over 3 is 60 degrees. What do we know about cosine 60? Cosine 60 is 1 over 2, right? Secant is its reciprocal, which is 2. Okay, what do we know about secant 0? Cosine 0 is 1. Secant 0 is 1 over 1 or 1. So here we have 4 times quantity 2 minus 1. So 4 times 1 or 4. So those derivatives, if you learn them really well in differentiation, you're also going to be strong as we go do the reverse process in anti-differentiation. And one more practice on finding antiderivatives, integral of u minus 2 over the square root of u. For this one, I would suggest that we break it apart write this as u over the square root of u minus 2 over the square root of u, and simplify each one. So the first one you can write as u to the 1/2 over basically u to the 1 minus a half, right? You're subtracting the powers there, so it'll be u to the 1/2. And the other one can be written as 2 times u to the negative 1/2. And we haven't integrated yet, so we're still going to integrate it from 1 to 4, but right now I'm just simplifying it. Okay, now that it's as simple as possible, we can go ahead and take the entire derivative. U to the 1/2 becomes u to the 3/2 over 3/2, or times 2/3, minus 2 times u to the negative 1/2. The entire derivative becomes, add 1 to the power, you get u to the 1/2, divide by 1/2, or that means same as multiply by 2. And now we can go from 1 to 4. So now we have 2/3 u to the 3/2 minus 4 times u to the 1/2, evaluated from 1 to 4. Plug in the upper limit first. So 2/3 times 4 to the 3/2, that's square root of 4, which is 2 to the 3rd, which is 8, minus 4 times square root of 4, which is 2. Okay, minus quantity. Now plug in a 1 everywhere you see a u. You're going to get 2/3. 1 to anything is 1. Minus 4 times 1 to 1/2, still 1. And the rest is just going to be simplification, right? 16/3 minus 8 minus 2/3 plus 4. Distribute your negative sign there. And there's a number of ways you could simplify this. Like, for example, 16/3 minus 2/3 is 14/3. And negative 8 plus 4 is minus 4. I will get common denominators. So here I have 14/3 minus 12/3. That's 2/3. And that is our final answer. So if the question is just a practice problem on integration, no need to graph it. Just use the common techniques we've learned about taking antiderivatives. And from there, plug in upper limit minus lower limit. And if there's no limits of integration, make sure you finish the problem by putting a plus c at the end, like we did over here. Okay, there's a few more things to cover in this lesson, but I'm going to reserve them till the next segment. See you next time.